Swiss countryside. And I'm told a story that in the late 13th century, 3 guys met in a field just like this and vowed to keep Switzerland free and neutral. Well, today that neutrality has crossed over into the world of science, where 300 feet below me, there are over 7,000 scientists working on the world's largest experiment that will give us a deeper understanding of the universe. CERN is the European Organization for Nuclear Research, where 34 countries from all over the world have put aside their differences to try to answer one fundamental question: what is the origin of our universe? CERN's focus is on building the LHC, or Large Hadron Collider. At 17 miles in circumference and crossing the French-Swiss border, the LHC will collide protons 800 million times a second, trying to get an inner glimpse of the atom. In total, there are 6 massive detectors built along the LHC, all designed to do one thing: study particle collision. This is where we come to ATLAS, the mammoth of detectors. When completed, ATLAS will be 150 feet long and 82 feet in diameter. This is Sarah.
Hi, Matt.
How are you doing?
Good, how are you?
I'm doing fantastic. So explain to me why you're building the world's largest roulette wheel.
Well, we have a lot of big questions, unanswered questions in physics. Our theories have gaps, and we're trying to fill in some of the gaps. And you need a big machine in order to do that.
Break the whole thing down for me. What exactly are you guys doing here?
Well, by colliding protons at very high energies, we're able to reach forces and, well, energies that people haven't been able to explore before.
So that's what you're doing. You guys are colliding protons.
Smashing them together and looking what comes out.
And you can't see a proton with the naked eye?
No, I've never seen one.
Okay,
No.
so how do you know you're colliding protons if you can't see them?
That's why you have all of this electronic equipment right here. There are a lot of big questions we're trying to answer. For one, we'd like to understand how all of the forces work that we've discovered in nature. Things like gravity and electricity and magnetism, we'd like to understand at a fundamental level. And we have some gaps in our understanding right now that we can maybe go after by going to higher energies. One real question we have is, why do particles have mass? And some of the particles we've found have mass, like electrons and protons.
Okay.
Some of the particles we've found don't have mass, like photons. So why is it that some particles have mass and some don't? And we don't understand why the particles that do have mass, why do they have the mass that they have?
If we understand why this one has mass and this one doesn't, who cares? What's the big deal?
Well, I have a couple answers for that. First of all, have you ever used electricity?
Yes.
Yeah, so learning about the electron was pretty useful, right?
Right.
When they found out about the electron, they didn't know what it was going to be used for. They didn't expect that someday we'd be turning on our lights necessarily, right? Turns out that we can do an awful lot knowing about electrons.
Right.
That's one way to look at this, is the things we haven't explored can teach us an awful lot. The real direct question is, how do these forces work? But the byproducts of it go into medicine, they go into learning about x-rays and equipment that you use when you go to the doctor.
So all these scientists, you guys are pretty much excited and anticipating answers to the unknown.
Oh yeah, I mean, this is one of those things where you can't believe that you were born at this time when this is going to turn on, and can't believe you're here.
I'm in the future. I can't stop staring at this thing. I'm Matt Rogers, and that is one really big thing. The LHC consists of over 100 million separate parts, all assembled above ground and then disassembled so they can be lowered into position. This 52-millimeter proton beam houses the particles as they glide around inside this 17-mile circle. I'm off to learn how they control something that no one has ever seen. You might be asking yourself why I'm riding a bike right now. Well, unlike my other little silly quirks, this actually has a purpose. You see, this is how the scientists get around down here. You can't have a choo-choo train without a railroad track, and you can't have a particle collider without an accelerator. How you doing? I'm Matt.
Hi, I'm Marina.
Marina? So tell me, this is the accelerator. So what does this do?
Well, what you see here are all these cylinders essentially, and these cylinders are magnets, the main constituents of an accelerator. This accelerator here at the LHC is a circular accelerator, so you need to bend the particles which are accelerating around and around and around to keep them on their circular orbit, and this is done by magnets.
So does it whip around several times before they collide?
Yes, of course.
So it's kind of like a slingshot, and we pull at more and more speed, and then boom.
More or less, yeah,
More or less?
why not, yeah. This accelerator is a collider, which means that we have two beams circling around the accelerator and colliding at 4 places.
In the pre-injector complex, the particles are prepared in smaller circular accelerators that increase the particle energy levels so that they can be injected into the LHC. It's kind of like speeding up on the freeway on-ramp.
And the most important thing, yeah, for us, like the accelerator physicists, are these 2 pipes.
These 2 in the middle.
Yeah, these are the beam pipes.
The beam pipes.
Yeah, there
Is that
we
where
have.
the particles go through?
Exactly, yeah. So in this beam pipe, the particles go in this direction, and in this beam pipe, the particles go in this direction.
Why do you crisscross them?
Because you want to make them collide at one point.
That would explain it.
Yeah.
I really ask good questions.
Well, you do actually.
I really feel like you've taken me inside. Now, this is obviously not put together. You're not going to leave it like this, right?
It's not put together yet. Yeah, you still have to do.
All right, me and you will do it when the cameras go off. Thank you very much. I appreciate it. I'm Matt Rogers, and this is not a really big thing. I went to the CMS detector to get a better understanding of how these things work. CMS is the second largest detector at the LHC. When it's completed, it will be 69 feet long, 52 feet in diameter, and weigh 12,500 tons. Explain the layers to me. Why is there so many layers on this?
So the detector itself is built up of pieces, and these pieces are arranged around the collision point of the beams as the layers of an onion might be. So you got layer after layer, and each of these layers corresponds to a detector element that has a particular task to do. And so as the particles that are generated in the collisions cross the detector, a succession of measurements takes place. And by measuring precisely how these particles are bent, we're able to determine the energy of the particles, okay? So the first layer of the onion, if you like, is the charged particle tracking detector. After that are layers of what we call colorimeters, different types of colorimeters to measure different types of particles. Then we get into the steel structure of the magnet, which has 2 jobs. One job is to contain and return the magnetic field lines, and the other job is to filter out all particles except for a specific type of particle which we call muon. And so the muons then fully traverse the steel structure. They are measured again in isolation by what we call muon chambers. These are some of the muon chambers that are interspersed in the layers of steel.
1 billion collision events will be generated in the detectors every second. After filtering that 1 second, only 100 collisions of interest will be recorded permanently. Because the LHC will generate 15 million gigabytes of data, it will require a total computing power equivalent to 100,000 PC processors. Currently, CERN only has 2,000 PCs. To solve this problem, they invented the Grid, a members-only lightning-speed internet that will spread the data all over the world. Okay, so I'm at the final piece of the big machine trifecta here at CERN. It's called ALICE. It's another huge particle collider, but how does it differ from the other 2? I don't know. But a scientist named Klaus is going to help me find out. Hey, Klaus!
Hey, Matt. Come on up.
I'll try. When ALICE is completed, she'll be 52 feet high, 85 feet long, and weigh 10,000 tons. She'll be taller than a 5-story building and heavier than the Eiffel Tower. Klaus!
Hi, Matt.
That was quite a journey, my friend. Am I in the nucleus of this thing, or what?
Yeah. So we're standing now in the middle of the ALICE detector.
Okay.
And this magnet that you see around us is the biggest conventional magnet in the world.
These are all magnets around us.
You are right inside the magnet.
Unbelievable. So how come, like, it's not sucking my microphone and all this other stuff?
It's not on now.
What would happen If you and me were wearing a metal jacket and you turned it on.
I think we'll be sucked out to the side.
To the side?
Yeah, I think so, but I'm not quite sure.
So this is the skeleton right now?
This is the skeleton. We built most of the detectors up on ground, take them down here and put them into this support frame that supports all the detectors of the experiment.
So this is actually going to stay
This is going to stay, but the scaffolding here is going to go out, and we'll put in a detector.
Why is this one different than the other ones?
This experiment is different than the other experiments at the collider because we're interested in colliding nuclei.
Okay.
While the other experiments at the collider are colliding protons. We shoot atomic nuclei and make them collide at a velocity very close to the speed of light. And we'll create a very high temperature, very high density volume, which will explode, and there will come particle flowing out in all directions in space. And this resembles what we believe was in the universe shortly after Big Bang. And we'll try to create this matter and understand how it behaves, what the properties and the structures of the matter is. We call it the little Big Bang because it's slightly smaller than the real Big Bang.
You can call it the baby Big Bang.
The baby Big Bang.
So when you say how hot does it have to be?
It's around 2 trillion degrees. So it's
2 trillion degrees.
It's 100,000 times hotter than the center of the sun. And the density of the matter we will create corresponds to taking the big pyramid in Egypt and squeezing it into a pinhead.
So it's safe to say that in about a year and a half from now, where we're standing will be 2 trillion degrees hot?
Yes.
That's pretty hot. I want to get out of here in time. Can you show me where you actually collide the particles?
It's right downstairs.
Let's go, please. By creating little baby bangs, we're rewinding the clocks of the universe back to its origin. While looking for the God particle that created matter, many other answers may be found. The particle collider might even be strong enough to produce black holes and create new dimensions.
Well, this is where the beam pipe will be installed. So we'll take off this small plate, we'll install the beam pipe here, and somewhere out here is where the actual collisions will take place.
Okay, so you're telling me that there's actually another tube out there somewhere that's going to come and connect with this?
Yeah. I mean, most of the 17-mile-long ring, we have 2 tubes. Okay. But in the regions around the experiments, these 2 tubes come together, and we'll only have 1 tube. And this is where the 2 beams come together and collide.
So when you collide, I mean, how many collisions do you have?
We'll have a collision rate of about 1,000 collisions per second. And each collision will create thousands of particles, which leave thousands of tracks in our detector.
So there you have it. I rode around with a physicist named Verena on the back of my bicycle in a huge tunnel, and I hung out with some very smart people in lab coats and hard hats. But we learned something very heavy, too. Basically, that atoms are the building block of all things. And by smashing the nucleus of the atoms and examining the particles, we could truly understand the universe. With that being said, I'll leave you with a quote from the great Albert Einstein and saying that the most incomprehensible thing about our world is that it is comprehensible. Now that is a really big thing.